In this lesson, we're going to look at combining volumes and molar volumes. The law of combining volumes says that when we have gases measured at the same temperature and pressure, those reactants and products will react in simple whole number ratios. So really, this is just another way of looking at balanced reactions that you learned how to do last year in Science 10. The first reaction you see here with nitrogen and hydrogen, if you were to balance it like you did last year, you would put a 1 in front of the nitrogen, and that would give you 2 nitrogen atoms. You would put a 2 in front of the ammonia to have 2 nitrogen atoms. That gives 6 hydrogen, so a 3 would go in front of the H2. So same thing as last year, we're just going to start looking at those coefficients a little differently. For the second reaction with carbon monoxide and oxygen, we're actually going to put a 2 in front of the carbon monoxide and 2 in front of the carbon dioxide. And then for the oxygens to balance, we need a total of 4 on both sides, so a 1 goes in front of the O2. Avogadro's theory says that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules and therefore equal numbers of moles. So when we balance this reaction of methane, 1 carbon on both sides, 4 hydrogen on the left, so a 2 in front of the water. Now we have 4 oxygen on the right, so a 2 in front of the O2. We can look at those coefficients as a couple of different things. They could be moles, so 1 mole of methane would react with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water. And we can also look at those numbers as volumes, say measured in liters. So 1 liter of methane would need to react with 2 liters of oxygen and would produce 1 liter of carbon dioxide and 2 liters of gaseous water. Let's do a couple of examples doing some calculations using that idea of the combining volumes. Nitrogen and chlorine gas react to form nitrogen trichloride. If 5.73 liters of nitrogen reacts at 120 kilopascals and a temperature of 369 Kelvin, what volume of chlorine is required to completely react with all of the nitrogen? We have some extra information in this question. The pressure and the temperature is going to stay constant, so really we can disregard those numbers. All we really need is the amount of nitrogen we started with and the balanced reaction, so we have those coefficients to work with. So our balanced reaction, nitrogen and chlorine, don't forget chlorine is Cl2, are going to produce nitrogen trichloride. Balance that so you have your coefficients and your ratio of all of those reactants and products. We're going to need a 2 in front of our nitrogen trichloride, a 1 in front of the nitrogen, and 3 in front of the chlorine. So now to calculate the volume of chlorine, Cl2, we're going to start with the 5.73 liters of nitrogen and multiply by our ratio of nitrogen and chlorine. So we want to cancel liters of nitrogen, and we want to end up with liters of chlorine. So from the balanced equation, we get our coefficients, 3 liters of chlorine for every 1 liter of nitrogen. Now my units for nitrogen cancel, and on your calculator when you put this in, you should get 17.19 liters, and we're going to round to 3 significant digits. So 17.2 liters of chlorine is your answer. Second example, propane is burned in a barbecue using oxygen gas from the atmosphere. What volumes of carbon dioxide and water vapor are produced at SATP conditions if 3.87 milliliters of propane are burned while you cook? Again, the conditions that we have isn't really going to matter. All we need is that volume of propane that we're starting with and the ratio that we get from our balanced equation. So propane, C3H8, burns in oxygen. So O2 is our second reactant, produces carbon dioxide and water. Balance that out. So 1 propane gives 3 carbons, so we need a 3 in front of the carbon dioxide. 8 hydrogens on the left means that we need a 4 in front of the water. We have a total of 6 plus 4 oxygen on the right-hand side, so that's 10. We need a 5 in front of the O2 on the left-hand side. So we want both volume of carbon dioxide and water vapor. So we'll do the carbon dioxide first, starting with the number that we know, which is 387 milliliters of propane. We can multiply by our ratio again that we get from our balanced reaction. We're looking for milliliters of CO2, so that goes on the top. And we're canceling the milliliters of propane, so that's going on the bottom. From the reaction, carbon dioxide, we get 3 for every 1 propane that we burned. So 387 times 3 divided by 1, and you'll get 1,161 milliliters. And because we want 3 significant digits, I'm going to change that into 1.16 liters as my final answer. Same idea with the water. So we're looking for volume of water, starting with 387 milliliters of propane times by the ratio from our balanced equation. So 4 moles or 4 milliliters of water for every 1 milliliter of C3H8 propane. Multiply the 387 times 4 over 1, and you would get 1548 milliliters. And again, for significant digits, I'm going to change that to 1.55 liters. Molar volume is an idea that relates the amount or moles of a gas to its volume. And this is generally done for specific conditions. All individual gas molecules take up the same amount of volume no matter what type of gas it is. So for any gas, we can determine the volume that's occupied by 1 mole of gas at a given temperature and pressure. For STP conditions, 1 mole will take up 22.4 liters. At SATP conditions, 1 mole will take up 24.8 liters. So a couple of example calculations so you can see these numbers and how they're used. What is the volume of 16.2 moles of ammonia gas at STP conditions? We're looking for volume, so we're going to calculate V. Starting with the 16.2 moles, we want to, again, multiply by a ratio so that we end up with volume. If we're looking for volume, that must mean that we want liters, so they need to go on the top. Moles will go on the bottom so that they cancel out. So now the liters and moles that is in our ratio is related to the molar volume that you see above. So for STP conditions, 22.4 liters for 1 mole. So 22.4 liters for every 1 mole. So now if you multiply, you get 363 liters as your answer. Second example, what is the mass of carbon monoxide gas in a 5-liter cylinder filled at SATP conditions? If we're looking for mass, and we know that molar volume is related to moles and volume, that tells us we're going to have to do 2 calculations here. So 5 liters of our gas, that's our volume. We could change that into moles using molar volume, and from there we'll be able to calculate mass. So we've got volume of carbon monoxide, so we're going to change it into moles, N. 5.00 liters times by our ratio so that we can change it into moles. Moles goes on the top, liters goes on the bottom. From your molar volumes, which were on the last page, SATP conditions says that there is 24.8 liters of a gas in every 1 mole. So if we do 5 liters divided by 24.8, you'll end up with 14.63 with some other trailing decimals moles. From that moles, now we can change into mass. So 14.63 moles with all of its decimals still in your calculator. We want to multiply so that we end up with units of grams because we're looking for a mass. We need to cancel moles, so those go on the bottom. Grams over moles is the unit for molar mass, so we need the molar mass for carbon monoxide. Carbon monoxide is CO, so you need to add together 12.01 for the carbon and 16.00 for the oxygen. So 28.01 is going to be our molar mass that we want to use. 28.01 grams for 1 mole. Multiply those two numbers together and your answer comes out to 410 grams for the mass of carbon monoxide.